Hello everyone and welcome to new discussion. In this lecture we are going to discuss about different types of vector data. As when we have been discussing definition of GIS, at that time I mentioned that data in GIS comes from variety of sources. So, and variety of formats also, that is why a manipulation word is also used. So, vector data, raster data, and there are different types of vectors and rasters, and also one more type is the TIN data along with your attribute data or non-spatial data. So, in this discussion we will focus on the vector data itself. As you know that this part just to connect with previous discussion is that real world which we can convert either into the vector or also in the raster like this. So, raster means we are having data in the grid form, and rasters are two types whereas vectors are three types. So, the real world, as you can see here, that if I want to convert into the vector, then there are three entities which we will also see in details, that point, line, polyline and polygon. So, through this we can have a representation of the real world in the vector domain. If you recall the history of GIS when we have been discussing, so initially the GIS was first developed to handle the vector data in the Canada, that is CGIS, and later on this raster capabilities also has entered into the GIS, and because of development on the digital elevation front, which is also one type of raster, and therefore GIS has become very powerful tool because of integration of vector, raster and one more type, the TIN data, which we will discuss sometime later. So, today our discussion is on the vector. Now, let me discuss everything in all types of data first in the GIS, that we have also discussed this point that there are two types of data in GIS, major two types. One is spatial data, another one is non-spatial data. So, spatial data includes vector data, raster data and TIN data, and your non-spatial data is mainly the attribute data or tabular data. And there are then different types of vectors, as also mentioned, that point, line or polyline and then polygon. So, three types of vectors are there. And though we have been familiar mainly with one type of vector, that is the line vector, in which we had the origin, we had the destination, and this used to decide what is the direction and magnitude of vector. But here in GIS we point data, line data, typical vector and polygon, all three are considered as vector data, because this is the discrete data, this is not continuous data. Like contour lines, topographic contour lines are discrete, they are representing equal heights or equal value along the line, but in between two contour lines you do not have any information. So, we call vector data as discrete data or discontinuous, whereas the raster data is continuous data. One cell of raster ends, another starts, and this is a continuous within that particular two-dimensional matrix or a grid. Raster two types, one is the grid type, another one is the image. There is slight differences between grid and images. So, when discussion will come on raster, we will discuss that part also. And the third type is, I have already mentioned, is the TIN. That is, TIN stands for triangulated irregular network. It is units here in TIN are triangles, whereas in raster units are square in shape, that means cells or pixels. So, if it is an image we call as pixel, if it is a grid we call as cell. So, the shape of the cell is always square in shape, whereas in case of TIN the shape of unit is always triangle of varying size and shapes. So, that is why it is called irregular network of triangles. So, triangulated irregular network, whereas in vector all are controlled by the coordinates. The coordinates are everywhere, because that is why the GIS is there to handle the geographic coordinate. Now, under this non-spatial category we are having various non-spatial types of data. One is the nominal or category data, then ordinal and ranks data. We will have separate discussion on this part also. Then interval data, ratio data and cyclic data, and last one is counts and amounts. So, these 6 types of non-spatial data so far have been implemented into GIS. If any new development take place in mathematical domain or computer science tomorrow, either in the representation of spatial data or non-spatial data, and if it is beneficial in GIS, definitely it would be incorporated in future as well. So, just to recap the entire gamut of data in GIS, that there are 2 basic types, spatial and non-spatial, and when we discuss the spatial, 3 subtypes, vector, raster and tin, and whereas non-spatial there are 6 types. So, let us come now focus on the vector data itself, that basically what it does, it allows users to specify specific spatial location. Spatial location again here is the geographic coordinates which we have discussed, and assume that geographic space is continuous, as you know, on the surface of or the globe. So, it is continuous, whether it is a land part or water body like a sea or oceans or land or any country or continent, it is all continuous throughout the globe. So, that is why the geographic space is continuous, and the same concept is also applicable in case of moon and Mars surfaces. There also the coordinate systems have been developed, so like for the earth also. So, it specify specific spatial locations. If it is a point data, it will have x and y in geographic locations, and then you can have n number of attributes associated with that particular point data, which is shown here as the point data. Then in polyline or line data, line features, we also call line features, there it is a string of xy coordinates and they are there. So, if we know the origin and we know the destination, we can find out the length, that becomes magnitude as well as the direction. And whereas polyline is the 2-dimensional entity, vector entity, where the begin point and end points are always same. So, it makes a complete polygon. We will see further details on this. So, in case of point data, the features or point features are stored as xy geographic coordinate pairs, and these nodes we also call that vertices, vertex, or in plural we say vertices, or node is a point that specify a position on a line for arc, polyline, polygons. So, even for point data, if I take this example of a line, so this is my begin point, this is my end point, and that is why you are seeing the arrows directions like this. So, now I know the magnitude, that is the length of this line becomes my magnitude, and the direction is also there. And so, these are the begin node, end node or vertex, and then in between you are having internodes as well. So, we call them as internodes. So, these blue dots are shown internodes. So, when a computer or GIS platform stores a line, what it does, basically it is storing xy coordinates all along the these lines or all vertices. So, it will store for begin coordinate and internodes or in between coordinates, and these wherever the bands are there or coordinates are there, and then the end one. So, that will make our this one. So, this is, as I have said, the begin code and the end code. Now, point is we say in GIS and we consider a point as a 0-dimensional vector entity. Why? Because a point is nothing but just an xy, a pair of n xy, a single xy, and therefore, you do not have anything to measure with the point. You cannot measure. Of course, between 2 points you can definitely measure the distance, but I am talking about a single point. So, single point will have just one pair of coordinate, that is x and y. Z value means that elevation value or any other attribute information will go as a non-spatial data in our system. So, point is a 0-dimensional entity Therefore, we cannot calculate or estimate its area, length or anything. Even on a GIS platform, if you are having a point data and if you keep zooming the point data, there will not be any size expansion of the point, because point does not have any dimension. So, it is only the location of a pair of coordinate, and then point normally represents a geographic feature and too small to be displayed as a line or area. Now, sometimes one may get confused about the scale. So, let me bring that discussion also here. Depending on the scale of map, suppose if I want to show the location of Roorkee within the boundary of India, then definitely it will come as a point, because I am displaying the whole India. So, my scale of my map is very small, and therefore, though Roorkee is having area, and within Roorkee IIT Roorkee also having its own area, but because of a small scale, the whole town would be shown as a just point data. That means a 0-dimensional entity, but you know in real sense it does not have, but as per scale it is represented. Whereas, if I am displaying a map of say Haridwar district, where Roorkee is part of Haridwar district, and then Roorkee will show as a polygon, not as a point, because the now scale is large. So, Roorkee can come as a area or polyline. So, instead of 0-dimensional entity, then it becomes a 2-dimensional entity. So, many things about the vector data will depend on the scale. So, this one has to really understand this thing. So, for example, a location of a building or location on a small map, water well or sampling sites, they all will appear. Even a location of village or town on a small scale map will appear as a point information. But we know in really point that is not a point, it has got its own area, but at a larger scale. This is one example is shown here, that there are 4 points are shown in XY coordinate system, and so far they are we are for simplicity we are not showing in geographic, but in software demonstration I would be showing in geographic coordinates too, just to keep things simple. And these tables which are shown are nothing but the attribute tables. So, for point 1, 2, 3, 4, there is a one pair x and y, and I can have the same table and different columns can have different information, or I can have a separate table. Here a separate table. So, against point 1, what is the location of what is the depth of a well, or point 2, 3 and 4. So, if I am having n number of points, I will have n number of rows in my table, and I can have theoretically n number of fields or columns in my table to store as much as information possible against a single point. So, here in example 4 informations we are already seeing the x, y, deep and amount. All these things are shown here in against all single points. Now, vector data types, say in this discussion that vector is composed of discrete coordinates. I have already told you that vector entities in GIS vector data are discrete, not continuous, and examples are point, line, polygons. Between 2 points you do not have any information, between 2 lines I gave the example of contours, you do not have any information, and polygons, within a polygon if the boundary is closed, then you do not have any information, except that you can do the measurements about the perimeter, you can do the measurement about the area, and one more information you can have about a polygon is the centroid. So, coordinates are typically provided in geographic format. This we have been already telling you, this is true throughout our discussion in GIS, that coordinates are in geographic domain or geographic coordinates, and some point features such as airplane locations need to also include a z value or height, and that will go as a attribute information, and you can have n number of attributes as we have discussed. But in some softwares like in ArcGIS, they also mention 3D points. So whenever it is mentioned 3D point, don't get confused. Point is a zero dimensional entity. So it doesn't have any dimension. So how this 3D point terminology has come? Whenever there is a term which is used in any software or literature, 3D points, that means the point is having x, y and z value also. But that z value will always be stored as a non-spatial information. So don't get confused. Same with the 3D line also. So that means along the line you are having height information or elevation information. So these objects must be modeled as 3D point features. So if we want to have all the time z value, it has to be stored as a non-spatial information in attribute table, whether it is a height of a plane or even depth of a well or any other information which requires a third dimension to be stored can be stored in that manner. Now 3D point features, as I have mentioned, they store basically z inside the geometry of their feature class, and this means that z values are automatically included with every new point features. Now this the third dimension value or z value can also come automatically if we are having in the background a say digital elevation model or a elevation surface. So whenever we pick or click a point, automatically from the background layer, which is a elevation surface, a z value can be included, and that can be stored against that point in a attribute table. Now the second entity among vector entities is the line or polylines. So this is instead of 0 dimension, now we are moving little higher in the dimensions, and this is called one dimensional object or entity. And if it is a straight line, then it is nothing but a begin point x1 y1 and x2 y2, or begin node end node, that is it, if it is a straight line. But if it is a polyline, I showed an example which was polyline. So we had in that one begin point, one end point or node, and in between we also had 3 internodes. So then that is called polyline. So whenever in the GIS terminology, whenever we say line, straight line means it will have just 2 pairs of x and y. And whenever we say polyline, that means it is having more than 2 pairs of x and y. So instead of simply calling as line, we call as polyline. And lines are having, as you know, a typical vector. Lines are having direction and magnitude, that is magnitude is equivalent to length, and hence a typical vector data. Now a set of ordered coordinates that represents the line or a shape or a feature, though it will not have width, but it will have only the line. That is why it is called single dimensional entity. Again, this is scale dependent. For example, generally in a map, say 50,000 scale or 250,000 scale, a road, canal, river, all these features are shown as a simple line. But we know in actual or in real world, the road will have its own width. A canal will also have width as well as depth, same with the rivers. So where that information will go, that information will be stored as attribute table. Like in case of 3D points, the z value was stored in 3D. So here also, not only the width of the road, you can store as many as information, attribute information, like when last the road was laid down, who was the contractor, who was the supervisor, who was the engineer, and how much it has cost, and so on and so forth. So against each road, that kind of information can be stored. But on a map, it will be, depending on the scale, it will be represented as a line, and that is a one dimensional entity. That means only we can measure the length of the line. not the width of the road or canal. That information always will go there. But however, if I am having large scale map, like I am having a map of Roorkee, there I can show the width of the road or canal or river with the real scale. So many times the scale, these entities are scale dependent, just you have to remember this thing. Lines is also synonymous with arc, with an arc, and that is why the this ArcInfo software, or is that word is still being continued as ArcInfo or ArcGIS. If I have to store a line like this line, there are one begin node and end node, and in between we are having two internodes. So they are stored now here, in order, because it is one step higher in degree about the complication. So instead of 0 dimension, now we are having 1 dimension. So many more information is required to be stored. So we will have a node table where all x and y's are stored. We will have another information about the line table where the first node and last nodes are stored. So if I take the segment 1, that is straight line between 1 and 3, then this first node is 1, another last node is 3. Similarly, when I come to the attribute or non-spatial information, then against A, I am some discharge value is written here, or flow value is written here, and then capacity is also written. Now it is not necessary this should always have a road or canal or river. While discussing who are users of GIS, I also told that electrical engineers have also started using GIS, and there they would like to know if there are different lines, they would like to know what kind of current is flowing and what is the capacity and so on and so forth. Including if they want to store, if that information is useful, like height of these lines, that can also be stored. The material of that line, that can also be stored as attribute table. So as we go higher and higher in vector entities, the number of tables will increase. That we will see little later in much more detail. Now sometimes we have to also, as when GIS started, it started basically for underground network, and still it is continuing, of course. So for underground features, the same way information can be stored, except that the depth is also stored instead of height. So some line features such as underground subway lines need also to include Z value or height to correctly locate themselves in 3D space. And these objects, that means underground lines, must be modeled again in the 3D line features. So that means the height is always attached as attribute of each line or each point. Basically line is made from continuous points which are interconnected. So the height value is stored against the point basically. So 3D features embed their Z values inside the geometry or a space field, and in softwares you will find 3D line. 3D lines that doesn't mean that you can measure the area of a line, not at all. 3D lines means it is also having Z value in it, and if it is not, it can be attached by bringing a digital elevation model or topographic surface below, and then collecting information about the Z value and putting in attribute table. So either you can automatically do it, or later on it can also be added in your line feature class. Line features, we have discussed few examples like underground transportation lines. Lot of networks now, power or OFC or telephone line or water supply, gas supply, all these are now underground network. So for that, GIS is very appropriate tool to maintain and to know where each network is there at different depth, and of course XY location also. Aircraft flight paths, because aircraft keep moving in altitude, not only X and Y but Z also. So these can also be stored. handled in GIS, line of sight between buildings or mountain and between two mountain or peaks, that can also be stored nicely. That can line of sight analysis can also be done. So, when we will be discussing GIS analysis part of this discussion will all come, or also called view set. And then transportation network inside skyscrapers. Lot of networks can be handled very nicely. Now, the third and last vector entity is the polygon, and also some literature will mention area instead of mentioning polygon, say area. Now, because it is a two-dimensional object. Why it is two-dimensional object? Because for polygon we can measure the area as well as the perimeter. So, that is why it is called two. Anything which for which I can measure the area, then it becomes two-dimensional. In case of line, I can measure only the length. So, that is why it is single dimension. In case of point, I cannot do any measurement specific to a single point. But of course, if there are 2 points, I can measure the distance between 2 points. That is a different thing. So, a polygon or polygons or area is a two-dimensional vector entity, and it is used to represent many features which are present on the surface of the earth as polygons. For example, land records or revenue records, revenue information that goes, different agriculture fields are there, different plots are there, they will be stored as polygons. Of course, here also the link of scale will come. If it is a too small scale, then polygons cannot be shown as polygon, you have to reduce and maybe even point, but when it is large scale, then polygon or the area can be shown in form of polygon. So, now as mentioned here, that an area is fully encompassed by a series of connected lines. And what does it mean? That if this is my begin node and I come back after that, so my begin node and end node has to be the same. Then only it makes an area and it closes the polyline. So, it is a higher version of polyline where the condition is that begin node and end node has to be same. So, here like x1 y1 and xn yn has to be the same. Whereas, in case of line or polyline, x1 y1 and xn yn need not to be the same. So, this you have to remember. Now, polygon is defined by lines that make up the boundary, as I have already drawn here, a point inside its boundary for identification that we also called as centroid, and polygons have attributes like point data can have attributes, line data or polyline data can have attributes. So, the polygon can also store, suppose if I am having revenue records or plot records. So, different plots are owned by different people. I want to store the area as well. I want to store the owner of the plot, whether it is already constructed a building or not. If a building is there, how many stories are there, how many people are living, and so on and so forth. All that information related with a single polygon can be stored as a non-spatial information. As you know that because lines have direction, it is a typical vector, and the system can determine the area that falls within the lines comprising the polygon. So, once it is closed, now we know which is the inside and what is the outside, and that gives the advantages about keeping the watch or information about the neighborhood. So, that is the best advantage of having vector data, because vector with line. So, begin node and end node, now you know that what is the direction, and once it is known, then you know who is outside and what is inside. Now, within one polygon you cannot have many details. All details are merged and single polygon, like for a land plot. Now, within land plot, unless I make further divisions, then otherwise I do not have any further boundary in it. So, each polygon contains only one type of data. For example, a polygon can contain a agriculture field So, one type of vegetation, though in the field there may be 2-3 vegetations, but if they are not marked or created a sub-polygon, I cannot show. So, that is that one thing one has to remember. Now, as we have seen examples of point data, how it is stored in the system, examples of line or polyline data, how it is stored. The major point here, the begin and end point is the same. So, it is a closed polyline, closed polyline. Now, you are again you will store as a node table, which is like this. So, all nodes are stored, their x and y is also stored. Now, this A is the polygon which is the inside one within the vector. So, it is having a node sequence starting from 1, 3 and last one is also 1, first one is also, because it has to be closed. Then only it can be called as polygon. If it is not closed, it is not polygon, it would be called as polyline. And then polygon A is because now it is a closed, so we can measure the area, we can measure the perimeter, or we can store as much as information which we would like to have for the polygon. Now, further we have to also store later on the information about the outside, that is the B. If I call as the outside polygon is B, then A polygon, which is the real polygon, outside one information will also be stored. So, when we will be going in further details about how system stores vector entities, we will also see that kind of thing. Again, like line, point, and they can have n number of, theoretically n number of attributes. So, the polygon. Why I am saying theoretically, why I am not saying all the time, because when we come for storing as many as or n number of attributes, say in case of ArcGIS in a simple database management system or like in Excel, we can have maximum 512 columns. So, that means I can store maximum 512 attributes against each line, point or polygon. But if I in some projects, if I have to store more than 512, then we have to come out and resort to some other database management system where this limit is not there. But there may be a limit of 1024 or whatever. So, somewhere theoretically no limit, otherwise practically depending on the software database management system, there might be some limit. But still 512 fields against each point, hardly any in any project we require. Even if we require and we do not have any other way to go for another database management system, there are ways. The best way, you store in 2 tables and these 2 tables can be related any time in your processing. So, you can have multiple tables, each is having 512 fields, no issue. So, there is a biomedia by which you can always handle more than 512 remaining in the same system. But currently this is what the support available. One more information which we sometimes for some particular studies that becomes very useful, that is the centroid, the center point of a polygon, that is called centroid. So, that is also stored or can be created automatically on a standard GIS software, and this information becomes many times very useful, because for a polygon which is a 2-dimensional entity, now you are having a point and you can attach many things with that point, and this point is unique for each polygon. So, again here begin and nodes are there, buttresses are there, and then you are having the boundary. So, you can measure area, you can measure the polygon and you can determine the centroid as well. Now, as I have already touched, but just to recap this thing, that polygon features have 2 separate parts that can potentially be modeled in 3D, their exterior perimeter line and their interior area. So, because outside is open, so there we cannot have perimeter. So, for inside we can definitely measure the area, but the information for outside is also stored. And in nearly all examples or instances, polygons should be modeled as 3D features only when then exterior perimeter needs to be included Z value. So, along with polygon also, but if a plot or a agricultural land having undulations, then against that plot only one single Z value will be stored. And you know, in real sense, in real world, there are undulations. So, if you want to store undulations, you have to have separate polygons, or there is another way of representing such thing is go and resort to the raster data rather than vector data or polygon data. And 3D polygon features mostly relate to areas that will basically help to define a surface. The surface and undulations can be best represented through the raster rather than vector, because vector is discontinuous. You know, the topographic surfaces are represented through polylines, that means the contours, isoheights, but in between contours you do not have any information. Though contours are representing elevation values also, but it is not a perfect solution to represent a surface. Instead, there is another model which is raster representation, by which we can represent the undulations, variations present within a surface. So, we should choose appropriately. But like lake boundaries, lake water is flat, we can consider very well, and therefore, a lake boundary can be represented as a polygon, no issue. But lake can have depth, and depth can be represented as a 3D polygon if that information is available. Same with the building footprints, in what area it has been constructed, the constructed part, and because building might have height, and therefore that information can be also stored as a 3D polygon, and there are many other such things can be stored. So, this brings to the end of discussion about the vector data. Just to recap everything about the vector, three basic entities. One is point, which is the simple zero dimensional entity. No measurements are possible, only it stores x and y coordinates. If you want to store z coordinates, it will go as a attribute value. Now, line or polyline is a one dimensional entity. You are having begin point, end point, or a begin node, end node, and if it is polyline, then x1, y1 and xn, yn. And here you can definitely measure the length, and of course, the direction is also known, because you know what is the origin, what is the destination. And in case of polygon, the first node and last node, that means the x1, y1 and xn, yn has to be the same, and then it is nothing but a closed polyline. And closed polyline, the advantage is a two-dimensional entity, and therefore, we can measure the area, perimeter, and also determine the centroid. Thank you very much.